Alright, so in this video we are going to talk about quantum spin for spin 1/2 particles. And a few examples of spin 1/2 particles are electrons, protons, and neutrons. There are other examples, but those are the most familiar. Now, the reason I'm making this video is that I find that when people talk about quantum spin, they use many analogies and they say that spin is like the particle is actually spinning, but not really, or they say that spin is like an angular momentum vector, but not really. And they go on and on about what spin is like, but they don't just say what it is. And I find this pretty frustrating because quantum spin is actually extremely simple. It's probably even simpler than angular momentum in classical mechanics. They could teach it to you in middle school if they wanted to, but for some reason they don't. Anyway, in this video, or maybe I should say series of videos, I'm going to tell you what quantum spin is, and I'm going to tell you how it works. I'm not just going to tell you what it's like, I'm going to tell you what it is. And the only thing that I'm going to ask that you know about ahead of time is complex numbers. So, just to remind you, we denote the real numbers with this special R symbol. And examples of real numbers are 0, 1, -4.35, 16 over 31, 4 minus 3 times pi. And a common notation that you'll see is that, for example, 4 minus 3 times pi is an element of the real numbers. So here, R denotes the set of all real numbers. And because 4 minus 3 times pi is a real number, it's an element of the set. Okay, so by contrast, this special C symbol denotes the complex numbers. And examples of complex numbers include, of course, I, 2 minus 3i, maybe, 17, for example, is a complex number, or 3 minus 42i. And if a and b are real numbers, so a and b are elements of the real numbers, then a plus b times I is a complex number. All right, so just to remind you, I guess I forgot to say this, but I squared is -1. So it's the imaginary unit. So yeah, every complex number can be written as a plus bi for some real numbers a and b. So now, let me just clear this a bit. One other thing I must remind you about the complex numbers is that if you have some complex number z, just a plus bi, so z is a complex number and a and b are real numbers, then we define z bar to be a minus bi. This is called the complex conjugate of z. Furthermore, we define the magnitude of z squared, so we have these two bars around z and we square it. This is defined to be z bar times z. So if z bar is a minus bi and z is a plus bi, then we can distribute this term into these two terms separately, and that's equal to a times a plus bi minus bi times a plus bi, and that's equal to a squared plus a times b times I minus b times, well, I guess maybe a better way to write that would be b times a times I, and then here we have plus, let me write minus b times I times b times I. So first things first, this term cancels with this term, and second thing second, because we have I squared equals -1, this immediately just becomes a squared plus b squared. So because a and b are both real numbers, a squared plus b squared is also a real number. And furthermore, a squared plus b squared is always going to be greater than or equal to 0. It's 0 if a and b are both 0, and it's greater than 0 if either a or b isn't 0. And that's going to be an important fact that we'll come back to later. Okay, that was just a little review of complex numbers. Hopefully you knew it, but it's good to just, be on the same footing. All right, now we're going to talk about vectors the way you're used to them. So the way you're used to vectors is, let's say you have a vector L, right? And we know it's a vector because I drew an arrow on top of L. And L is given by 3 numbers, which we'll call Lx, Ly, and Lz. And these 3 numbers are the 3 components of the vector. So Lx, Ly, and Lz are all real numbers. That means that the vector L is an element of a set which we call R3. Now, R3 is just the set of 3-dimensional vectors with real components. That's just how we denote it. Now, another way that we could write L is we could write it as the vector L equals Lx times I hat plus Ly times j hat plus Lz times k hat. Now I hat is just the vector which is 1, 0, 0. J hat is the vector which is 0, 1, 0. And k hat is the vector which is 0, 0, 1. And these 3 vectors, I hat, j hat, and k hat, are all basis vectors. So that means that any vector in R3, so any vector in R3, can be written as a combination of I hat, j hat, and k hat. Whoops. Now let's clear away the screen. All right. So these vectors also have something called a dot product. So if you have one vector v, which has components vx, vy, and vz, and you have another vector u, which has components ux, uy, and uz, then v dot u is equal to vx times ux plus vy times uy plus vz times uz. And notice that v dot u is equal to u dot v. So the dot product is what we call symmetric. Furthermore, v dot u is just a single real number. So we say v dot u is an element of the real numbers. V dot u isn't a vector, it's just one number. All right, now the next thing I want to say is that we can find out what the dot products between the basis vectors are. So for example, I hat dot I hat is 1, and I hat dot j hat is 0. Furthermore, I hat dot k hat is 0, j hat dot j hat is 1, j hat dot k hat is 0, and k hat dot k hat is 1. So this is all the dot products between all the different basis vectors. So this means that we can use the dot product along with the basis vectors to find the components of all of our vectors. So for instance, v sub x, which is the x component of our vector v, is just equal to v dot I hat. And furthermore, v sub y is equal to v dot j hat, and v sub z is equal to v dot k hat. So roughly speaking, the dot product measures how much two vectors point in the same direction. So let me draw two sets of vectors. So these two vectors are going to have a bigger dot product than these two vectors, because these two vectors basically point in the same direction, they're almost parallel, whereas these two vectors are pointing in very different directions and they're almost orthogonal to each other. So one way to say it is that the dot product measures how much two vectors overlap, roughly speaking. All right, so after all of that, we're finally going to talk about quantum spin. So how quantum spin is different from the regular way of thinking about vectors. So there are two huge differences. So the first difference is that quantum spin vectors are two-dimensional, not three-dimensional. All right? So they only take two numbers to specify, not three numbers. That's the first difference. And the second difference is quantum spin vectors have complex components, not real. So in other words, quantum spin vectors are elements of C2, not R3. That's pretty weird. So it takes two complex numbers to specify a quantum spin vector instead of three real numbers. Now, there are also many notational differences. And if you want to understand what everybody else is writing, you got to understand the notation. So to start off, usually we write the basis vectors as I hat, j hat, and k hat. But when we're talking about spin, the basis vectors are written as follows. That and that. Now you should read these as spin up and spin down. Now this thing, this line and then this bracket, this thing is called a ket. It's just called that. And we put like a little thing inside the ket. Here we have an up arrow or a down arrow. These are really just labels. Or maybe you can even think of them as stickers if you like. So whereas we would usually write a vector v as vx I hat plus vy j hat plus vz k hat, where v is an element of R3, we would now write psi. That's the Greek letter psi. Physicists just like to use this letter for no particular reason. It just looks pretty cool. Anyway, this is a vector. Right, this is equal to alpha times the spin up vector plus beta times the spin down vector, where psi, where the psi vector is an element of C2, and alpha and beta are each complex numbers. The main thing I want you to take away from all this is that even though spin is weird, mathematically speaking, it's actually pretty easy. It's really basically just the same thing as regular vectors, except for the fact that they're two-dimensional and they have complex components instead of real components. The math itself is pretty simple. All right, so now I'm going to clear this. Whoops. All right, so now we're going to talk about one other tiny little thing, column vectors, which is just the way grown-ups write vectors. So really is actually, it's very simple. Okay, so this spin-up vector, right? Grown-ups write it with a 1 on top of a 0. And they write the spin-down vector with a 0 on top of a 1. This is exactly the same thing as writing, I hat is 1, comma, 0, j hat as 0, 1, 0, and k hat as 0, 0, 1. The only difference is one number is on top of the other number instead of the numbers going from left to right. Now, why do grown-ups write them as these columns, these column vectors? I don't know. I mean, I think it looks a little cooler, but yeah, I don't know. It's just the way they do it. So you got to know this. So, right. So just to really hammer it home, instead of writing, actually maybe I should. Right. So if we were to write psi equals alpha spin up plus beta spin down, that would be equal to alpha, and then the spin up vector has a 1 on top of a 0, and the beta vector has a 0 on top of a 1, and that's just equal to the vector with an alpha on top of a beta, which is in C2. Whereas you might be used to writing a vector v as vx I hat plus vy j hat plus vz k hat, which is equal to vx comma vy comma vz, which is an element of R3. All right, now take all of that in while I erase the screen. I know it's just been a lot of notation, but you got to know the notation. So just try your best. All right. So the next thing we have to talk about is the so-called inner product, which is basically more or less like the dot product. So remember that v dot u equals vx ux plus vy uy plus vz uz. Now, let's say you were to have psi1, which has components of alpha 1 and beta 1, and which is an element of C2, and you were to have psi2, which has components alpha 2 and beta 2, and which was also an element of C2. Now, the way that you write the dot product here is not like that, right? Like I'm not even gonna keep that on the screen because it's just like so wrong. Right, how you write it is as follows. It's kind of spiffy notation, but you flip one of the brackets and you kind of put them together like this, right? And this is called the inner product of psi1 and psi2, and it's equal to the following thing. So alpha 2 bar complex conjugation times alpha 1 plus beta 2 bar times beta 1. Now, just as v dot u was just a single real number, the inner product of psi 2 and psi 1 is a single complex number. Now, I want to point out one difference with the regular inner product. As you remember, v dot u is equal to u dot v. We said the dot product is symmetric. Here, this inner product isn't exactly symmetric. So if I write psi 1 on the left, right? So here I have psi 1 on the left, here I have psi 1 on the right. The inner product here is actually alpha 1 bar times alpha 2 plus beta 1 bar times beta 2. And that is equal to the complex conjugate of psi 2 and psi 1. So we don't exactly have that so the dot product is exactly symmetric, but with this inner product we've defined here, it's almost symmetric, but you have to complex conjugate the whole thing. All right. So that is that's the inner product. Okay. So there's one more piece of math I got to tell you. And I know it's getting a little bit tiring, but it's actually pretty exciting if you're learning this for the first time. If you're not, I apologize, but now once you know this, you're going to be able to read a lot more things. All right, so now we're going to talk about dual vectors. And it sounds scary, but really it's not. So I told you that we write our vectors as column vectors. So psi here has components of alpha and beta. Let me just actually write column vector. Now, dual vectors, you might be pleased to note, are written the way you would normally expect vectors to be written. from left to right. So actually, let me just write this here. If I just write it, it'll seem less scary than if I try to explain it. So here I have a row vector. Here I have the numbers written in a row. Usually you don't write the comma like you would normally write. But yeah, okay, here's the point though. You can take a vector and turn it into its dual vector by changing this bracket here and making it this bracket here, sort of like mirroring the brackets, and also turning it from a column vector into a row vector, and also complex conjugating the components. Now there's some very silly names for these things. So a vector, as I said earlier, is called a ket. And all right, so let me actually just say that these names and basically all this notation was invented by a guy named Dirac, who you might have heard of. So okay, so get ready. Okay, so he calls these vectors kets. All right, now you're like, why is it called a ket? Doesn't make any sense. All right, it's about to make sense. All right, now he calls these dual vectors bras. Yeah, he calls them bras. So why did he call them bras and kets, right? Well, you might have guessed it, but if you put a dual vector next to a vector, this whole thing is called a bracket or a bracket because it's an inner product and it's in between these two brackets. I know. So make of that what you will. If you've ever, if you're familiar at all with matrix multiplication, let me actually just write all this out. Oh, sorry. So if you're familiar at all with matrix multiplication, you might recognize this as I think it's a 2x1 matrix. I'm trying to think if it's 1x2 or 2x1. I'm pretty sure it's 2x1. So yeah, this vector here is a 2x1 matrix, and this dual vector is a 1x2 matrix. And if you carry out, if you don't know what matrices are, don't worry, by the way. I'm just saying for those of you who do know what matrices are. But if you carry out the matrix multiplication, this whole thing is a 1x1 matrix, which is just a number. So yeah, okay. There's been a lot of notation, but the point is that you can make a vector into a dual vector by complex conjugating the elements and writing them in a little row. And if you put a vector next to a dual vector and you just sort of write them out like that, that's really just the same thing as the inner product the way I wrote it before. Now you're saying, well, okay, well, what was the point of talking about these dual vectors? Well, it kind of helps you, work out, steps a little bit easier. We'll make use of these dual vectors throughout the video. I just wanted to let you know what they were. They're really nothing scary. If you don't really get, like, why did I write this row vector next to this column vector like this and then declare that, like, it's this number, it's really just a rule. It's really nothing more than that. All right, so that's enough math. Now we are finally going to talk about physics. So, measurements and probability. So, in physics, there are two types of people. There are experimenters and there are theorists. Now, when it comes to spin, experimenters are only allowed to ask one question. So, experimenter can ask, is an electron, let's say our particle is an electron, is an electron spin up or spin down with respect to a particular axis. Right, so by axis I mean an axis in space, like the x-axis, the y-axis, or the z-axis. So this is the only question an experimenter can ask, and there are only two possible answers, right? It can either be spin up or spin down. Now, the theorist, at best, can only say, I can give you the probabilities of the electron being spin up or spin down but I can't say for sure which it will be. So the theorist can't tell the experimenter whether it's going to be up or down with 100% certainty. All they can say is it's this percent chance that it's going to be spin up or this percent chance that it's going to be spin down. So this is the best you can do in quantum mechanics. So let me explain the setup. So here I am drawing the z-axis. Here's the z-axis. And right here, chilling right here, we have some electron. And the electron has some state. I'm going to start calling this thing, this vector, a state vector. And it has components alpha and beta. And here we have the experimenter. So they have a clipboard and they have on safety goggles, and as per lab rules they have to have their hair back in a ponytail, and they also have to have closed-toed shoes. And the experimenter is asking, and the experimenter also has some sort of device. So I'm not going to go into details as to what this device is, but this device is going to be able to answer the question of, is the electron spin up or down, right? So here's the experimenter, and they're asking, is the electron spin up or spin down with respect to the z-axis? So that is what they're asking. Now you might be asking, wait a second, how does this device actually work? Like, how do you actually figure out if an electron is spin up or spin down? And to that I say, I'm not going to tell you right now. I'm going to talk more about the measurement process in a later video, but for right now, just focus on the math. Alright, so what is the probability that the electron is going to be spin up or spin down? Well, first off, if our state psi is in the spin up state, which is equal to 1, 0, then there's a 100% chance that it's going to be measured to be up, and a 0% chance that it's going to be measured to be down. If psi is in the spin down state, which is equal to 0, 1, then there's a 0% chance that it's going to be measured to be spin up, and a 100% chance that it's going to be measured to be spin down. And in the most general case, if psi is equal to alpha times spin up plus beta times spin down, meaning its components are alpha and beta, then the magnitude of alpha squared is going to be the probability that it's measured to be spin up, and the magnitude of beta squared is going to be the probability that it's going to be measured to be spin down. Now, notice that the probability that the electron is spin up plus the probability that the electron is spin down has to be equal to 1. And that's because there's only two possible outcomes. Now, the condition that the magnitude of alpha squared plus magnitude of beta squared is 1 can be written a little bit differently as follows. Notice that the inner product of psi with itself, which we can write using our row vectors and column vectors as follows, equals alpha bar times alpha plus beta bar times beta, which is equal to the absolute value of alpha squared plus the absolute value of beta squared. That has to also be equal to 1. So we can see that the condition that the inner product of psi with itself being equal to 1 is the same thing as the condition that all probabilities sum to 1. Now we're going to clear the screen and we're going to write all this another way. So notice that the inner product of the spin up vector with psi, which we can write as follows, is just equal to alpha. And the inner product of the spin down vector with psi, which we can write like this, is equal to beta. So the probability that we have spin up along the z-axis is just the absolute value of the inner product of the up of the spin up state with psi squared, right? Because that's just equal to the absolute value of alpha squared. And the probability that we have spin down along the z-axis is equal to the absolute value of the inner product of the spin down state with psi squared, because that's just equal to beta squared. All right, so clearing the screen again, you might be asking yourself, what's so special about the z-axis? What if I want to measure the spin along the x-axis or the y-axis? So now we're going to talk about other axes. So let's talk about the state that's always spin up along the x-axis. I'm going to denote that with this up arrow and this x in the subscript. So you might wonder, what is the state such that when you measure it along the x-axis, it'll always be spin up? And you can't really guess it, so I'm just going to tell you what this state is. You just have to believe me for a few moments. It's the state where the components are 1 over root 2 and 1 over root 2. You're saying, well, that's pretty weird. Now, what's the state that's always down in the x-axis? That's the state with components 1 over root 2 and negative 1 over root 2. And you say, huh, okay, that's pretty weird. What's the state that's always spin up in the y-axis? I'll write it here. So spin up along the y-axis, that's the state with components 1 over root 2 and I over root 2. All right, so now we're finally really using the imaginary numbers here. And what's the state that's always spin down in the y direction? Well, that's the state with components 1 over root 2 and negative I over root 2. Finally, just for completion, as you know, the state that's always spin up in the z-axis has components 1 and 0, and the state that's always spin down in the z-axis has components 0 and 1. Now you might be wondering, why are there so many square root of 2's everywhere? And that just gets back to what we were discussing earlier, that the inner product of a state with itself has to be equal to 1 so that all the probabilities sum to 1. So, for instance, the inner product of the spin-up state along the x-axis with itself is equal to 1 over, well, it's just equal to this, which is equal to this, which is equal to a half plus a half, which is equal to 1, just as we need. Let's clear this away. Let's also do the example of the spin up state with respect to the y-axis and see what the inner product of that is with itself. So remember that when we take the dual vector, this thing right here is the dual vector, we got to complex conjugate the components. So this is equal to the dual vector with components 1 over root 2 and negative I over root 2. Right, so you see that here the second component was I over root 2. We gotta complex conjugate it when we take the dual vector. So it becomes negative I over root 2. So all right. That's just equal to that. Which is equal to that. Which is once again equal to 1/2 plus 1/2, which is equal to 1. All right, so clearing this once again, I want to ask one more question, which is, what is the inner product of the spin up vectors and the spin down vectors along each axis? So what is the inner product of the spin up vector along the x-axis with the spin down vector along the x-axis? Well, that's just equal to that, which is equal to that, which is just equal to 0, right, because of the minus sign. Likewise, you might already know where this is going, but let's also take the inner product of the spin up state with the spin down state along the y-axis, and taking the dual vector of the spin up state along the y-axis. Remember, we have to complex conjugate. So the I becomes a negative I, and now putting in the spin down vector here, we see that we have another negative I from that, and that's equal to this, and negative I times negative I, well, that's just the same as I times I, which is equal to negative 1. So here we have 1/2 minus 1/2, which is also equal to 0. And finally, as we already know, the spin up state along the z-axis and the spin down state along the z-axis um, also have an inner product of 0. So in any axis, the spin up state has an inner product of 0 with the spin down state. All right, so having cleared the screen and done all that algebra, I'm now going to answer the question. What is the probability, if you have a state psi, that when you measure its spin along the x-axis, you will measure its spin to be spin up? So the probability that you measure spin up along the x-axis is just the absolute value of the inner product of the spin up state along the x-axis with psi squared. Likewise, the probability that you measure spin down along the x-axis is the same thing, but you got to use the spin down vector along the x-axis instead. Likewise, the probability that you measure spin up along the y-axis is the same thing, but now you got to use the spin up state along the y-axis. That is a y. And the probability that you measure spin down along the y-axis is the same thing, but now you got to use the spin down vector along the y-axis. And this is exactly as you remember. This fits in with what we saw earlier, that the probability of measuring spin up along the z-axis is just this, the absolute value of the inner product of the spin up state along the z-axis with psi squared. It's a bit of a mouthful. And the probability of measuring spin down along the z-axis is just this. All right, so let's clear some of this up. And I want to make a very important point. Whether a particle has a definite spin, so by definite spin I mean it's either 100% up or down, depends on what axis you're measuring the spin. So, for example, the state that has definite spin up along the x-axis doesn't have definite spin up along the z-axis, right? Because we can just quickly calculate that the probability of measuring spin up along the z-axis is just going to be the following number, which is just root 1 over root 2 squared, which is just a half, which is 50%, right? So, you know, whether or not this state has a definite spin or not depends on what axis you're measuring the spin. If you measure it on the x-axis, it has definite spin. It's 100% always spin up. But if you measure it on the z-axis, then 50% of the time you're going to find it spin up, and 50% of the time you're going to find that it's spin down. This actually, I think this is a good time to just give one piece of terminology. So, the spin up state along the x-axis can be written as follows: as 1 over root 2 times the spin up state along the z-axis plus 1 over root 2 times the spin down state along the z-axis. And this right here, when we have a state that's a sum of two other states, we call this a superposition, which you might have heard before. That's just a word we use. So we could say that the spin-up state along the x-axis is in a superposition of a spin-up state along the z-axis and a spin-down state along the z-axis. So that's just, I just wanted to explain what that word meant. It's really nothing too complicated. All right. All right, now I want to go through an example. So I want to calculate all of the expectation values along all of the axes for the following state, which is 3/5 spin up plus I times 4/5 spin down. So we're going to calculate the expectation values that it's spin up along the x-axis, spin down along the x-axis, spin up along the y-axis, spin down along the y-axis, spin up along the z-axis, and spin down along the z-axis. And if you don't want to see this, just skip this part. First things first, I want to check to make sure that this state really does, the inner product of the state with itself really is 1. So remember that you got a complex conjugate for the row vector, for the dual vector. And the idea is, for this is that if you want to, you can pause the video and work this stuff out for yourself and see if your answers agree with mine. Just so everybody's on the same page. Nine over 25 plus 16 over 25. And 9 plus 16 is 25. So this is 1. And okay, so this is a good state to talk about. All right, so let's start with the probability that it's spin up in the x direction. I'm really concentrating here. All right, so the probability that it's spin up in the x-axis is 50%. Now you can already figure out, just from the fact that all the probabilities have to add up to 1, that the probability that this is going to be spin down in the x-axis is also has to be 50%. But even though we already know what the answer is, I just want to work it out just so you really are convinced. So this is just all right. So this is just equal to 50% as we knew it had to be. Now we're going to calculate the probability that it's going to be spin up in the y direction, and that's going to be given by this. Negative, okay. So I times negative I is just 1. So all in all, this is 7 over 5 root 2 squared, which is 49 over 25 times 2, which is 49 over 50, which is equal to 98%. So that's actually kind of interesting that it's almost, but not quite, 100% to be spin up in the y direction. And that's basically because the vector that's spin up in the y direction is this vector. And as you can see, this vector is actually very similar to this vector. And the inner product between two vectors is basically the overlap between the two vectors, or how much they're the same. And because those two vectors are almost exactly the same, we can see that this vector we've written down is almost perfectly pointing in the y direction, upwards. So because we know that the probabilities have to sum to 100%, we know that the probability that we measure a spin down in the y direction, that has to be 2%. But it's good to check the math anyway. Makes you feel responsible. All right. So that's that. And I squared is equal to -1. So this is equal to the absolute value of -1 over 5 root 2 squared, which is equal to 1 over 50, which is equal to 2%, which is exactly what it had to be. But it's good to confirm it anyway. All right. Now, the z-axis is definitely the easiest one. So the probability that it's spin up in the z-axis is just equal to 3/5 squared, which is equal to 9 over 25ths. Multiplying the numerator and the denominator by 4, we see that this is 36%. So now we're going to calculate the probability that it's spin down in the z direction. And that's just equal to 4/5 squared, which is equal to 16 over 25, and multiplying the top and the bottom by 4 once again, we find that this is equal to 64%, which is just what it had to be so that all the probabilities sum to 100%. All right, so now we're done with that example. And now there's one last really important thing I want to talk about, and that is collapse. So after a measurement is performed, something really important happens, and that is that your state will collapse onto whatever it was measured to be. So let's just say our state started out as alpha times spin up plus beta times spin down. And we know that there is a magnitude of alpha squared % chance that's going to be measured to be spin up, and there is a magnitude of beta squared % chance it's going to be measured to be spin down. And if it's measured to be spin up, then after the measurement is performed, the state will then be equal to the spin up state. And if the state is measured to be spin down, then after the measurement is performed, the state will be measured to be spin down. And what this means is that if you conduct the same measurement a bunch of times over and over, you're going to always get the same answer. So if you were then to measure again, is it spin up? So okay, let's say the first time you measured it, you found that it was spin up. If you then measured it again, there would be a 100% chance that it would be spin up again. And then your state would still be the up state. Likewise, if you measured the first time that it was spin down, there's a 100% chance that if you conduct the same measurement again, that the state will be spin down, and then the state will remain spin down. So I want to say a few things about collapse. The first thing is, why is it called collapse? Like, what is the word, like what image does the word collapse evoke? So the picture a lot of people have in their minds is that the psi vector has a component along the spin up axis and the spin down axis. And the idea is that after the measurement is performed, the vector psi will either collapse onto its component along the spin up direction if it's measured to be spin up, or it will collapse onto the spin down vector. And it's, maybe you can think of it like a piece of furniture or a folding chair or something, like collapsing. So that's why it's called collapse. The second really important thing I want to say is that collapse is what prevents an experimenter from figuring out the quantum state of a system to arbitrary precision. So you might think that, well, even though I can only calculate the probability that the state psi is measured to be up or down, maybe if I measure it a bunch of times and I measure it in many different axes, I can calculate, okay, how many times do I get spin up and spin down, and I can find what those probabilities are, and I can then pin down what alpha and beta are by doing a bunch of measurements. But quantum collapse prevents you from doing that, because if you keep doing the same measurement over and over, you're going to keep getting the same answer over and over. The thing is that in quantum mechanics, after you do a measurement, your state is altered due to the measurement. And this is quite different than what we're used to in classical mechanics. So, I mean, even though it's the case that in real life, if you try to measure something in some way, you're usually going to have to alter the thing you're measuring, there's no law of classical physics that measuring something has to somehow alter the object that you're measuring. But in quantum mechanics, it really is the case that if you measure something, you are going to alter the thing that you're measuring. All right, now that I've talked about quantum measurement collapse, I can now tell you about something pretty funny about quantum spin. So let's say you start with an electron, which is completely in the spin-up state in the z direction. And let's say you were to measure the spin of this electron along the x-axis. Now, 50% of the time, you're going to measure the spin to be up, and then the electron will collapse to the spin up state in the x direction. And 50% of the time, you're going to measure it to be spin down, and then your electron state will collapse to the spin down direction, to the spin down state in the x direction. But now let's say after you measure it along the x-axis, you then measure it along the z-axis. And remember that originally, if you were to have just measured this along the z-axis, 100% of the time, you would have found that it was spin up. But now, because you did a measurement in between, because you measured it along the x-axis in between, you're going to find that 50% of the time, it'll be spin up, and 50% of the time, it'll be spin down. And this will be the case no matter what the intermediate measurement said. So here we can see a really clear demonstration of how performing a measurement changes the quantum state due to quantum collapse. If you didn't do this intermediate x-axis measurement, you would have just got spin up 100% of the time and spin down 0% of the time. But because you did this intermediate measurement, you will now find that 50% of the time it'll be spin up, which are these two possibilities, and 50% of the time it'll be spin down, which are these two possibilities. Now, there's one thing that might bother you about this whole collapse situation, which is that, as I've described it, quantum collapse seems instantaneous. It seems as though there's one precise point at which the state is measured and it collapses onto one of its basis states. And we have this sense that in physics and in life in general, nothing is truly instantaneous, that measurements take some interval of time and that there isn't one exact time at which something is measured. So you might be wondering what's going on with that. And all I want to say is that instinct to say that nothing is instantaneous is actually correct, and that measurements do take a bit of time. And in a later video, I'm going to talk more about measurements in general, because it's definitely one of the most intricate parts of quantum mechanics. And that these measurements truly aren't instantaneous. So that's all I'm going to say about that for right now. Wow, so we've talked about a lot in this video, but I still have a few more things to say that didn't get covered yet. So here are my final stray remarks. Okay, say that you have a state psi with components alpha and beta, and say that you have some complex number z such that the absolute value of z is 1, right? Now say that you take z and you multiply psi by z. So now the state z times psi has components z alpha and z beta. The thing is that the state psi and z times psi have no observable differences. So here's what I mean. If you want to measure the spin of psi along the x direction, the probability that it has spin up is just that, right? If you want to measure the probability that z psi has spin up along the x direction, then the probability that it's going to have spin up is equal to this. And it's a little weird notation, but all it means is that z psi is now the state that you're computing the inner product with the spin up state in the x direction. But the thing is that, and if you really write it out, you'll see this for yourself, but you can just pull the z out of the brackets, and this is just equal to z out front, and then the inner product of the spin-up state along the x direction with psi. And then the absolute value of two complex numbers multiplied with each other is equal to the product of the absolute value of those two complex numbers. So this is just equal to that. But because we know that the absolute value of z is 1, we know that the probability of measuring spin up along the x direction is just this. But this is the same as this. So the probability of measuring spin up along the x direction for this state is the exact same for this state. And this doesn't only work for spin up along the x direction, it actually works for any measurement along any axis. This is a general fact that psi and z times psi have no observable differences. They are in some sense the exact same state. So that's one pretty important thing to mention. So I want to talk about something else, which is that at the beginning of the video, I said that we were restricting our attention to spin 1/2 particles. So what does this term spin a half really mean? And it turns out that's actually a pretty complicated question. And the answer to this question, I would say, lies in a branch of mathematics called representation theory, which is far beyond the scope of this video. This would take many, many videos to talk about. But the spins that a particle could have are 0, 1/2, 1, 3/2, 2, 5/2, and so on and on. And the main thing to say about it is that our spin state psi were elements of C2, right? But if you have a general spin S, right, that's not necessarily a half, it turns out that instead of being two-dimensional, these vectors have dimension 2s plus 1. So if s equals 0, then 2s plus 1 equals 1, right? And states live in C1. But these are actually extremely boring because all of our states need to have norm 1. A one-dimensional vector with norm 1 is just nothing interesting about that. Now if you have spin a half, which is what we've been talking about this whole video, then 2s plus 1 equals 2, and then states live in C2, and that's decently interesting. It's taken up this whole video to talk about that. If s equals 1, then 2s plus 1 equals 3, and then states live in C3. And if s equals 3/2, then 2s plus 1 equals 4, and our states are elements of C4, and on and on and on. Now, while I'm talking about these other spins, there's something, I think this thing is actually going to be the last thing I'm going to talk about in this video, which is angular momentum. So even though I haven't really talked about angular momentum at all in this video, spin and angular momentum are very closely related. So in quantum mechanics, angular momentum comes quantized in units of h bar. So what do I mean quantized units of h bar? I mean that you can only measure the angular momentum of an object in integer multiples of h bar. So let me explain what this means. So for a spin 0 particle, right? So spin 0 particle, the angular momentum along any axis is always going to be 0 for that particle. But for a spin 1/2 particle, the angular momentum could be minus h bar over 2 if the particle has spin down along that axis, or just plus h bar over 2 if the particle has spin up along that direction. For a spin 1 particle, the angular momentum could be minus h bar, 0, or h bar. For a spin 3/2 particle, the angular momentum could be minus 3/2 h bar, minus 1/2 h bar, 1/2, oh no, 1/2 of h bar, or 3/2 times h bar. And the thing is that they always go in steps of h bar, right? So from minus 1/2 h bar to plus 1/2 h bar is an h bar jump, right? So the same thing. It's h bar, h bar, h bar, you add h bar, you add h bar, you add h bar. So, I mean, if you've never seen this before, you might be thinking, well, wait, why is, this is, you're just telling me this. Like, why is this really true? It's actually a very interesting question, but this isn't really the appropriate place to talk about it, seeing as we've just gone through this enormous video. Okay, so I hope you learned something about spin. It's actually extremely interesting. Even though it takes a while to explain, honestly, the math is pretty simple. I mean, the most complicated thing about it is that you have complex numbers. In the next videos, I'm going to talk about the Pauli spin matrices, expectation values. That should definitely be pretty interesting. And then I'm going to talk about how spin changes in the presence of a magnetic field, so the dynamics of a spinning particle, how the spin state changes in time. And after that, hopefully, I'm going to talk about quantum measurement. So I hope you stick around for those videos, and thank you for watching.